Question 7 is an interesting collisions question. So instead of our traditional just like two balls hitting each other, we've actually have this collisions question kind of in the context of particle physics almost. So basically we have we have a solid which is modeled by a two-dimensional lattice, so it's like this little square of balls, and they're all of mass m, and a piece of it can temporarily be moved out of its position, but it's quickly returned to the position by the forces that hold the solid together. So, for example, this little sphere Q here, it could move away, but it'll very quickly be moved back by some force. And then an incoming particle P of mass 2m, which moves with the speed of u, it collides with Q obliquely, which is at rest of the outer surface. So that's just like a normal collisions question. It's just these two balls hitting each other. And the line joining the centers of the particles at the point of impact is along the I-axis. So we're not going to have to do that ourselves because, of course, to deal with an oblique collision, the first thing we have to do is make sure that kind of one of the axes is joining their centers when they collide. And the reason for that is because their centers are joined by the I-axis, when they hit each other, they're actually only going to transfer the I velocity. The Y or the J velocity won't be affected. It's not going to actually change its velocity up or down for either of them. And before the collision, the direction of P makes an angle theta with the I-axis. And then afterwards, it's turned through an angle of theta such that it makes an angle of 2 theta. And the coefficient of restitution is 2/3. So basically what that means is if we have P here, I'll draw a little diagram to help visualize it. And so we have P, and it's moving here with velocity of u. And we have the I-axis here. And this angle here is theta. Well, then it's going to be turned by an angle of theta. So basically, that means it's going to, this line here, this kind of vector, is going to be turned by an angle of theta. So it's obviously not turned this way. It's not turned downwards, because if it was turned downwards, that would just be parallel. So it must be turned upwards. And then this angle here must be 2 theta, because if we just have a look at, if that arrow continued, the velocity continued, we'd have theta here. But then since it's turned by an angle of theta, it's also turned by this much. It's turned by this theta as well, such that the total angle, this is the final velocity of P by an angle of 2 theta in total. So I like to draw up a little table like this just so that we can see exactly what's going on and use the information. So before the impact, we have sphere P. So basically, if we just resolve into the velocity into I and j, so we have our u here, and then we have our theta here. So this will be u cos theta. This one here will be u sine theta. So quite straightforward. The initial velocity of P is u cos theta i's plus u sine theta j. Thankfully, we don't have to worry about the signs because they're both just moving up and to the right. The initial velocity of Q, we're told that Q begins at rest. So the initial velocity of Q is just 0. Afterwards, P will be, well, we said that we'll have this VP is what we can call it. We can call the final velocity of P VP. And then we know that this angle here will be 2 theta, which means this will be VP cos 2 theta. And this one will be VP sine 2 theta. And we're going to write this sine 2 theta and cos 2 theta. We're going to write those just in terms of cos theta and sine theta by using the double angle formulae. The reason being, we're looking for tan theta. So if we have this sine 2 theta and cos 2 theta, that's going to kind of make it a bit harder to find tan theta unless they magically cancelled out, but they probably won't. We want to be able to kind of maneuver this cos 2 theta and use it with the cos theta. So we're going to be breaking these down using the double angle formulae. So on page 14 of the formulae and tables booklet, you can see we have cos 2a is equal to this and sine 2a equals this. You could do this further on, but the thing is it kind of gets messy and then you have to change them. But if we do it now, a nice few things will cancel out. So basically afterwards for P, in the I direction, we'll have VP, then instead of cos 2 theta, I'm going to write that as cos squared theta minus sine squared theta. So cos squared theta minus sine squared theta. And that's in the I direction. And then plus, because we're still going up and to the right, VP times, and then we'll have, instead of sine 2 theta, I'm going to say 2 sine theta cos theta. And that's in the J direction. And then for Q, since Q's velocity was initially 0, and the J velocity is not going to be changed, we're just going to have final velocity, we can just call it VQ, and that's going to be going in the I direction, and there'll be no J's. So in any oblique collision question, we're kind of using 3 facts. The first one is that the velocity in the I direction, or the initial velocity in the I direction, or in the J direction, sorry, is equal to the final velocity in the J direction. So obviously it's not very interesting for Q. The initial velocity in the J direction is 0 and afterwards it's 0. But for P it's useful. It helps us to get a relationship between VP and U and stuff. So what we'll have is that U sine theta, which is the initial velocity in the J direction, equals 2 VP sine theta cos theta. I just kind of put the 2 to the start because it works easier. And then this is why I wanted to write them as thetas instead of leaving them as 2 thetas. Now we can cancel the signs, so we already get a little bit of simplification. That U is 2 VP cos theta. And that's our first kind of important fact from our first equation. We're told nothing about energy, so that means the other two things we're going to use, and we are told about the coefficient of restitution, so we can use that here in Newton's experimental law. And then we also assume, as long as no energy is lost, we almost, well, in basically every oblique collisions question, we also use the conservation of momentum, unless for whatever reason they say you can't, but they probably won't. So we'll start off with conservation of momentum. It's usually just what I do first. I usually just do them in this order. So we'll have that the initial velocity, and we can, because the momentum is actually going to be conserved in the J direction as well, but the thing is, because the initial momentum in the J direction here is 0, and since these velocities are the same for P in the J direction as well, we don't actually get any new information by including the J direction, because the velocities all stay the same. So we can just apply this in the I direction, and it'll just work out to be a bit simpler, because we don't need to take into account the J direction. You can if you want, but this is just less work. So we're going to do the conservation of momentum in the I direction. So we'll have the mass of P times the initial velocity of P plus mass of Q times the initial velocity of Q equals the mass of P times the final velocity of P plus the mass of Q times the final velocity of Q. This is all just in the I direction, by the way. So for P, the mass of P is 2m, it says here. So we'll have 2m. And then the initial velocity of P in the I direction is u cos theta. We'll have u cos theta. The initial velocity of Q is 0, so this entire term is just going to be gone. So we can just have equals. Then the mass of P again is 2m. The final velocity of P is, where is it here? It's going to be Vp times cos squared theta minus sine squared theta. So we'll have Vp times cos squared theta minus sine squared theta. And then finally, we'll have plus the mass of Q is just m, and then the final velocity of Q we're just calling Vq. We can do some simplifications here. We can divide across by m, so we'll get the 2u cos theta equals 2Vp times cos squared theta minus, say the theta, minus sine squared theta plus Vq. That's our second important equation. You can kind of do substitutions now if you want, but I usually like to do them at the end. I like to write out all my equations first, then look at the substitutions, just to keep track of it all, so that you're not doing the wrong substitutions or you're forgetting to do one. That's what's Newton's experimental law, which is just for the coefficient of restitution. So Newton's experimental law says that the relative velocity of P, or the velocity of P relative to Q, is going to be the coefficient of restitution times the initial velocity of P minus the initial velocity of Q, with the minus before the e to show that we're going the other direction. So we can just sub in the numbers. The final velocity of P, again, we're just talking about the I direction, is Vp cos squared theta minus sine squared theta. Vp times cos squared theta minus sine squared theta. And then Vq is just Vq equals minus e, which is minus 2/3, times the initial velocity of P is u cos theta. And then the initial velocity of Q is nothing, so we just leave it like that. And that's our second equation, which we don't really need to simplify from here. And now what we can see is we have a u here, we have a u in this equation, so I guess the first thing we could eliminate is that, because remember, we're just looking for tan theta, so we can replace the u with 2Vp cos theta in each case. So we're going to have used this, so we don't need to worry about this one anymore. So now if we look at equation 2, and we're subbing in for u, we'll have 2 times, and then we'll have u, and u is just 2Vp cos theta, 2Vp cos theta, times cos theta, equals 2Vp, and if we expand out these brackets now, because we see that we have a cos squared theta here, so we could get some nice cancellations going. So 2Vp cos squared theta minus 2Vp sine squared theta. And then we'll just have plus VQ. We can get some more simplifications if we bring this. So here we'll have 4 VP cos squared theta. Here we have 2 VP cos squared theta. Bring that to the other side. We'll get 2 VP cos squared theta equals VQ minus 2 VP sine squared theta. And we can also notice something nice. If we bring that sine squared theta to the other side, what we'll have is 2 VP, factor that out, and then we get cos squared theta plus sine squared theta equals VQ. One of the trigonometric identities is that cos squared plus sine squared is 1, so you get the 2 VP equals VQ. So very nice equation there. And then we can use this equation in our final equation, this third one. So we can replace the VQ with 2 VP, and we can replace the U with this. So we'll kind of do this in steps, I suppose. First of all, we'll replace the U with 2 VP cos theta. So now we're going to look at equation 3, and what we're going to leave the VP for now. We'll have VP times cos squared theta minus sine squared theta minus VQ equals minus 2/3 times, and instead of U, I'm going to write 2 VP cos theta, 2 VP cos theta, and then that's times cos theta as well. And now we also see we can replace that VQ here with 2 VP, which we can do now as well. And I'll expand this out as well, just because you can see we'll get similar cancellations because we have 2 VP cos squared theta here. So if we expand this out, we get VP cos squared theta minus VP sine squared theta minus, and instead of VQ, I'm going to write 2 VP equals minus 2/3. Well, I can say minus 4/3 because we have the 2 in the bracket as well. Minus 4/3 VP cos squared theta. Our VPs are all going to cancel if we just divide everything by a VP. And then we can bring this, I guess if we multiply by 3, it'll make the calculation a bit easier. So we'll have 3 cos squared theta minus 3 sine squared theta minus 6, because this minus 2 VP is gone, multiply it by 3, equals minus 4 cos squared theta. And now we can simplify. We kind of start to see this taking shape. So if we bring, I guess we could bring this cos squared theta to the other side. We'll get 7 cos squared theta. So we'll have 7 cos squared theta. I guess we could bring the sine squared to the other side. It doesn't really matter. We'll just leave them all on the left side. Why not? Minus 3 sine squared theta minus 6 equals 0. Now, since we're looking for tan, we're looking for tan theta. So if we divide by this cos squared theta, it'll help us out, and you'll see that why now. So then we'll get 7 minus 3 sine squared over cos squared is just tan squared theta. And then 1 over cos squared, when we do this 6 over cos squared, that's the same as saying 6 sec squared theta equals 0. And on page 13 of the formulae and tables, this is that sec squared is 1 plus tan squared. So I can replace this. We'll have 7 minus 3 tan squared theta minus 6. Instead of sec squared, you can say 1 plus tan squared theta equals 0. Then we get 7 minus 3 tan squared theta minus 6 tan squared theta equals 0. 7 minus 6 is 1 minus 9 tan squared theta. Now you can see it kind of coming together, equals 0. Bring the tan squared theta to the other side. 1 equals 9 tan squared theta. Divide by 9 on both sides. We'll get 1/9 is equal to tan squared theta, which means square root both sides, you get that tan theta equals the square root of 1/9 is 1/3. And that's what we were asked to prove. In part 2, we're asked to calculate the I and j components of the velocity of q after the collision in terms of u. So the only thing we should have on this is u. So if we go back up here, the velocity of q after the collision is just vqi plus 0j. So what we're going to have is we're going to have vqi plus 0j. So we just need to figure out what vq is in terms of u. And we can do this using the work we did up here. So first of all, we know that vq is just 2vp. So this is the same as 2vpi plus 0j. Now, do we know anything about vp? Well, we know that u is 2vp cos theta. So I'll copy that down. So you could just write that this is the factor you're using. So we know that u is 2vp cos theta. That means that vp equals, divide by 2 cos theta on both sides, u over 2 cos theta. So we get that this is equal to, so we'll have 2 times vp, which is just u over 2 cos theta, I plus 0j. The 2's will cancel, and we'll just get u over cos theta I plus 0j. We know what theta is. We could solve this equation for theta and then just calculate cos of that angle. But the smarter thing to do that's more accurate is if we draw a right angled triangle, and we have theta here, then tan is opposite over adjacent. So this is opposite over adjacent. The hypotenuse will be 1 squared plus 3 squared. So it'll be square root of 10. You might want to show your workings on that. Then cos of theta, that means, is adjacent over hypotenuse, which is 3 over 10, over root 10. And finally, we'll have equals u, and then over, and then cos theta is just 3 over root 10. 3 over root 10. And that's all in the denominator, that's in the I direction, plus 0j. You can either recognize that dividing by a fraction is the same as flipping the fraction, or if you multiply the top and bottom of this fraction by root 10, so times root 10 times root 10, and we can do that because root 10 over root 10 is 1. So what we get is you get u root 10 over 3 over root 10 times root 10, they cancel. You just get 3i plus 0j. And that's the answer for, we might want to state it. This is velocity of q. So we'll have vq, the final velocity of q. I suppose you could call it, maybe not like that, because vq in our case represented this. So maybe we could just say final velocity of q equals that. In part 3, we start to bring in a bit of work and energy and stuff into it. So after the collision, Q experiences a restoring force, F, which is proportional to X, the displacement of Q from its initial position, where K is the constant of proportionality. In case you don't know what that means, it's the same as the restoring force of basically a spring on a particle when it's stretched through a displacement of X. So basically what it means is if we have Q here, and let's say, remember, because Q is a part of the particle, what happens is if Q moves to here, let's say it moves a distance of x, so this is x, then there's a restoring force, so there's going to be a force pushing Q, so this is Q after the collision, there's going to be a force pushing Q back towards its original position. So there's going to be a force which is going to be proportional to x, so this force will be proportional to x, or in other words, the force is equal to kx. Constant times x, where k is the constant of proportionality. So this is basically just Hooke's law. It's like when you're deriving, I'm sure you kind of do the proof in one of the calculus chapters or in the work and energy one, that when you have like a spring or like an elastic string, when you stretch it out, you look at the work done by it because it's not a constant force. So since it's not a constant force, we can't just say F equals, or sorry, not F, we're looking for work. So work is Fs, but that's only for a constant force. So we're not going to use that. Instead, we have to use the one that's not for a constant force, which is this one, the integral of force with respect to displacement. So here our only force is kx is our only force. We don't have to worry about the sign because work is it's a scalar quantity, so we don't want it to be negative. So our work is going to be the integral, and then our force is kx, and we're doing that with respect to x, because x is the displacement. If you just integrate that, we'll get that kx squared over 2. That's our work, plus c. And now how will we figure out what the c is? Well, think about it. Let's say x is 0. Let's say the displacement is 0, and that the q after this red sphere is here. How much work has it done? Well, it's done no work because it hasn't moved. So when x is 0, w is 0. So we know when x is 0, w is 0. Therefore, we have w equals kx squared. We have w equals kx squared over 2 plus c. We know that we can say 0 equals k times 0 squared over 2 plus c. That means that c is just equal to 0. Therefore, the work done is given by just kx squared over 2. And that's the answer. In part 4, we're asked to find the maximum displacement of Q from its initial position in terms of m, k, and u. So in order to figure this out, let's think about what happened. So again, we have Q, and Q has no energy at the start. Remember, Q is at rest. It literally has no energy, or at least in our model it has no energy. But then it's hit by the particle P, and that gives it kinetic energy, which is given by, remember, the kinetic energy is given by mv squared over 2, or half mv squared. And it's given this kinetic energy, and then as it continues to move, so obviously with kinetic energy it's going to be moving, as it continues to move, this restoring force up here, that's going to be slowing it down. That's going to be causing it to decelerate. And then eventually it's going to keep going until the force has slowed it down so that it stops moving and then it starts going back towards its initial position. And when it gets to that final point, the kinetic energy is 0. So basically we need to find how much work do we have to do to make that kinetic energy equal to 0. So first of all, what is our kinetic energy? We're told it is in terms of mk and u. So remember, for q, our final velocity is u root 10 over 3. So our kinetic energy will be m, now remember the mass of q is just m anyway, m over 2 times, and then v squared, well, v is, what was it again, u root 10 over 3. So what we'll get is we'll get 10u squared over 9. We can simplify that a bit more. We can say that's going to be 10 mu squared over 18, which is the same as 5 mu squared over 9. And basically, we need our restoring force to do this much work in order to make it stop. And of course, when it stops, then it's for the furthest away, and then it starts going back. So we want to let the work done by this equal to this. So we want our kx squared over 2 to be equal to 5 mu squared over 9. We want that much work to be done. And then we're looking for the maximum displacement. So we'll just solve for x. We'll get that kx squared equals 10 mu squared over 9. So that we get x squared is equal to 10 mu squared over 9k. Square root both sides, you get the displacement, and since we're going right, it will be positive, equals the square root of 10 mu squared over 9k. We can factor out some things if you want. You don't have to, but I think it's nice to. You can factor out the u squared and the 9, so we'll get u over 3 times the square root of 10 m over k. And that will be the final displacement, the maximum displacement. Max displacement. And that's the question done.